السلام عليكم ورحمة الله وبركاته.
وعليكم السلام. وعليكم.
Yes, let's start chapter 5 today, and this is the announcement which is already on the WhatsApp and also on the Blackboard announcement.
Teacher,
Yes, please.
I have a question.
Please go ahead.
How many marks will be in the quiz?
Actually, in the system, normally before the midterm, you have 5 marks for quiz before the midterm, 5 marks, and after the midterm 5 marks quiz. But since we are conducting 2 quizzes before the midterm, so you can say in the system it will be 2.5 marks, but in the quiz itself you may have 5 or 7 or 10. So I will take the average out of 2.5, the first quiz and the second, and we will add out of 5 in the system after second quiz, inshallah, before midterm. Similarly after
So
midterm.
each quiz has 2.5 per month?
Aywa.
Okay, thank you.
Welcome.
Teacher, period Wednesday, period 7.
Sorry?
And period 8.
Sorry?
Class. We have a class period 8.
Of course.
Wednesday and Wednesday.
Yeah.
Period 7. Yeah.
Yes.
After that we have class.
Of course, there is nothing written here that you don't have class. You have the class, of course. You have class, of course.
Of course, we have a class. Okay, but can you put it to the period class? Period A is quiz?
No, because if there is some technical issues and if I take the last period, so you'll be in trouble. You cannot attend the next class. On the safe side, we keep it in period 7. So if we finish properly and excellently, it's fine. We will study some other material in chapter 8. But if there is something wrong, so still we have time to fix that. That's why I keep it in period 7. Okay.
Good. Yes, good.
Thank you.
Teacher.
Yes.
The quiz tomorrow. Can I make it with the mobile phone?
Tomorrow? Who told you tomorrow? أنت نوم الآن؟ كل وقت نوم ها؟
What?
شوف سكرين، شوف سلايد. ما في بكرة. يوم الأربعاء الأسبوع القادم إن شاء الله.
صح. Yes. You, yes.
Good morning. You woke up. Yes. Chapter number 5. Work and energy. I'm speaking, I'm running. Why? Because I ate good lunch in the form of chemical energy, so I have energy to do the work. So the energy I took as food, that is in form of the chemical energy, I'm speaking. This is the sound energy, okay, and you are listening that sound. I eat this chemical food, chemical energy. I am walking, I am converting it into mechanical energy, for example, kinetic energy, okay? Right. So everything needs energy to do work, whether it's the human beings, animals, even the machines. Your laptop needs energy to work. Your mobile phone needs charging once it is finished. So it needs energy, it needs chemical food, you see? I am writing and you can see it. This is the light energy. So energy, what is energy? As I said, the capacity of an object to do work. Okay? Right. Okay? What you call in Arabic? طاقة. صح. Okay. Right. It's the capacity. Capacity means قابلية. It's the ability of an object to do work. Forms of energy. As I said, mechanical energy. We will focus in this chapter on mechanical energy. And mechanical energy, we have two types. Kinetic, when it is associated, when it is linked with motion. I am moving, I have kinetic energy. And the second type of mechanical energy is called a potential energy, which is linked with this, which is associated with position. For example, if some object is going up or down, if height is increasing, its potential energy is increasing. Its height is decreasing, coming down, its potential energy is decreasing. We will discuss all these things in detail, especially mechanical energy. As I told you, in this chapter we will focus on these two, kinetic energy and potential energy. But still we have other energies we will not discuss in this chapter, by the way, but still we have chemical energy. As I told you, the food we eat, that's in form of the chemical energy. The battery dry cell you use in different appliances, that is in form of the chemical energy. Electromagnetic energy, light is a form of electromagnetic. Microwave, right, radio waves, some other ways, they are they fall in the spectrum of electromagnetic. Infrared, all these things. Nuclear energy, you know, atom as a whole is a neutral particle. In the center we have proton and neutron, okay, and outside electrons are moving with very high speed. So the energy hidden in the atom, we call it nuclear energy. We cannot see atoms with our naked eye, but subhanallah, we have tremendous amount of energy within the atom. You might have heard about the nuclear energy. Even the Saudi Arabia have taken the initiative to work on the nuclear power plants. So we will be producing electricity with the help of nuclear power plants. So the energy which is hidden inside the atom, we will use some sort of specific the elements, and we will be enriching them, and we will use that as a fuel in the power plant to generate electricity. Energy can be transformed from one form to another. This is what I already discussed with you. For example, I am eating food, I am taking the chemical energy. I'm speaking, I'm converting that chemical energy into sound energy. I'm walking, I have kinetic energy, so I'm converting chemical energy into kinetic energy. You have electrical energy. Once you press the switch on for electrical heater, electrical energy is converted into heat energy. If you turn on the light in the room, you are converting electrical energy into light energy. Okay, you have loudspeakers, you are speaking, sound energy is converted into electrical signals, but then from the the loudspeaker, it gives you again from electrical signal into the sound energy, so you can hear. Can be used in place of Newton's laws to solve a certain problems more simply. You see, whenever we have equations of motion we did in chapter number 2 and 3, projectile motion, vectors and scalars. So all these laws and equations we need to solve motion problems of different objects. So similarly, these rules for the energy, equations for the energy will help further to solve problems. All right. Work. You see, when you have an object, for example, this block, its initial position is here, x sub I, you apply the force F and it will move to the right, and you bring it at final position, so delta x is equal to final position minus initial position, right? So when a force F acts on an object and it covers some displacement delta x, as you might have seen here, we say that work is done. So work is a scalar quantity. It doesn't have direction, only the magnitudes. This is the rule. You remember you did in chapter number 3, A vector dot B vector, right? That was equal to A, magnitude of A multiplied by magnitude of B multiplied by cosine of angle between the two. Okay, instead of A you have F, instead of B you have delta x. Okay, and this is cosine theta. So this is the rule where F is the magnitude of the force, delta x, as I told you, magnitude of the object's displacement, and theta is the angle between the force and displacement vector, right? SI unit of work is joule, whereas the unit of force is Newton, okay, and the unit of delta x displacement is meter. So Newton meter, we call it joule. So when 1 Newton force acts on an object and moves it through 1 meter, we say that 1 joule work is done on that object. All right. Now, you see, we have seen that work is equal to force delta x cosine of theta. You see, delta x or d is the same meaning, which is displacement. For example, a person is moving a lawnmower with force F, making some angle theta below the x-axis. So this is d, this is force, and you can find out the work done by the person once you are given the value for the force in newtons, the value of displacement dr delta x in meter, and theta in degrees. You see, when work is equal to, now a person is standing by applying force upward by his hand on this briefcase. He is standing, not moving. How much is the displacement? 0. So delta x or d is 0. When delta x or d is 0, the work done will be 0. Here in C part, yes please. Yes. This is B. What is displacement?
0. Just I asked you about theta.
Whatever theta, it will be 0. What will be 0? Because 0 multiplied by S, even you have theta 0 or 1 or 10 or 20 or 360. This is 0, so khalas, 0. Okay? Right?
Right, thank you.
Okay. And if you ask someone to take heavy load and move some distance, for example, I say, okay, 500 meter. And then once he finishes work, he will ask for his labor charges. He will ask for the money. You would say, no money for you, because you did nothing. Your work done is 0. Why? Because F delta x cosine 90. Cosine 90, how much? 0. So the work done, how much?
0.
In the language of physics, the work done is 0. If someone is applying force upward and taking some load, some weight up to some displacement, in physics we say 0. But that labor will ask for the money, right? But in physics, work done is 0, right? Please have a look for 2-3 minutes. Try to figure out, write down what is given, write down what to find out, use the previous rule, which is work is equal to F delta x cosine theta, and just figure out. Take 2 minutes. Yes, so let's start this question now. An Eskimo returning from a successful fishing trip pulls a sled. Okay, this is the sled. The total mass is given to you and force is given. Okay, this is the force. By pulling on the rope. A part, how much work does he do on the sled if the rope is horizontal? Horizontal mean when the sled, this one, and the rope in man's hand like this one. So displacement and force in the same direction. So theta is 0 in part A. And he pulls the sled 5 meters. So displacement is 5 meter and force 1.20 10 raised to power 2 Newton. So you have to find out first the work done, force, displacement, cosine of theta. This is force, displacement 5 meter, and cosine, how much? Theta is 0. So you get the work done 600 joules. Is it okay? Good.
Yes, okay. Teacher, can you repeat, please?
No problem.
Thank you.
Okay. Now, you see, this is the rule for work we just finished.
Yes.
Now, force is given to you. Okay, this is the force. This is force. Delta x given to you 5 meter. 5 meter. Cosine theta. Theta is 0 because he is saying by pulling on how much work does he do on the sled if the rope is horizontal to the ground. Okay, this figure is for B part, in fact. So for A part, theta is 0 because force and displacement in the same direction. Okay, force and delta x in the same direction. Oh, sorry. Okay, right. So force and delta x are in the same direction. So theta is 0. Okay, so cosine 0 here. So cosine 0, once you use the calculator, cosine 0 will give you 1.
Okay.
Thank you.
Thank you.
Welcome. Now, B part. How much work does he do on the sled if theta is 30 degrees? Right? Now we use the same rule. $5 you get 520 joule. Alhamdulillah. يهديكم الله. Now C part then. Any question?
Yes, please. Why is this answer?
What's the answer in the book?
The answer is 6.00 multiply 10 over 2.
Okay, it's the same by the way. You see here, this one I can write 60 multiplied by 10 raised to power 1 or 6.00 10 raised to power 2 or 0.6 times 10 raised to power 3. All are the same by the way. Okay, what we do, if I shift this decimal point here, it will be 60. So multiply by 10 raised to power 1. If I shift decimal point instead of 1, 2 points, so 10 raised to power 2. This is what I wrote it here, 6 multiplied by 10 raised to power 2. If I shift decimal point here after third digit, so 0.6, 10 raised to power 3. 1, 2, 3. You get the point?
That's it.
If you use the calculator, all these will be equivalent. Okay. Similarly here, this is 520. If I write 52.10 raised to power 1 or 5.2 10 raised to power 2, all are the same, right? Let's move to the C part then. At a coordinate position 12.4 meter, okay, the Eskimo lets up on the applied force. Okay, so this is your x sub I, okay, initial position. A frictional force, we use small f. For applied force we use capital F, and for the force of friction we use small f. 45 Newton. And the sled, so a frictional force 45 Newton between the ice and the sled, bring the sled to rest, mean it comes to rest finally. Okay, how much rest at coordinate? So this is your final position. So delta x, let's calculate. Final 18.2 minus initial, so you get delta x, how much? Yes, 18.2 minus 12.4, you get 5.8. okay, this is delta x. So you see, what is the rule? Rule says work done is equal to force multiplied by delta x and cosine of theta. You see, motion on the right and force of friction on the left. What is the angle? 180 degree. And keep in mind, applied force we use capital F, and the force of friction small f. So I would write here small f. Okay, all right. So 45 Newton.
Teacher, how you get to 180?
Sorry,
How you get to 180?
I'm telling you, motion on this side, sir,
Yes.
and force of friction on the other sides. What is the angle between two? 180. If they are on the same direction, then angle will be 0. If they are like this one, angle will be 90, right? If they are like this one, for example, again the angle is 90, sir. So 45 delta x is 5.8, and cosine of, could you please calculate and let me know the answer? Minus 261 joule. You see, minus, I'm going to tell you the idea. Even before solving, you must know that how much work done by the force of friction. You see, for the work done by the force of friction is always in opposite direction to the motion. So that's why you have the negative sign. Negative sign means opposite direction. It's not compulsory that it is always negative. For example, if you are moving on the left side, force of friction will be on the right side, because here you have negative, here positive. So if you have motion on the negative x-axis, force of friction will be along positive. So in that case, it will be that case. Anyhow, so this is your minus 261 joule. Please make sure in some books the unit is written N, Newton. If you see Newton, that is wrong. Write joule, J. You have J in the book or N? J, good.
Excuse me, teacher.
Please.
You write minus 261 because the FK.
Yes. Actually, I am using the basic rule. Ma nizam. What's the rule? Fx cosine theta. Theta is 180 degree. And if you use the calculator cosine 180, you will get minus 1. Any question? Next. Work kinetic energy theorem. Kinetic energy. You see, energy associated with the motion of an object. You see, if a person, right, moving with velocity, 2 meters per second, whereas its mass is equal to 60 kg, it will be having this rule: kinetic energy Ke, kinetic energy half multiplied by is the m multiplied by the square of the speed of the object. Okay, in this case is if you have half mv square, m how much, 60, v square, so you would get 120 joule, the energy, which is called the kinetic energy. Kinetic means moving due to motion. So due to motion of the object, we have energy called kinetic energy. It's the scalar quantity with the same unit as the work, which is joule. So the unit of work and unit of energy or kinetic energy, same unit, joule. For example, a person is standing here having the mass 70 kg. What is his kinetic energy? Yes? 0, because standing mean his speed is 0, so kinetic energy will be 0. Right. Now we have work kinetic energy theorem. The work done on an object by net force is equal to the work done, the net work done, or the total work done on an object is equal to change in its kinetic energy, change delta, change in its kinetic energy. So whenever you have delta, mean always final minus initial. So final kinetic energy minus initial kinetic energy, you get change in kinetic energy, which is equal to the work done. Alright. So for example, you have this object here. Initial velocity Vi are V0 and final velocity Vf are simply V. You apply the force, you travel displacement delta x, and this is the work done we have seen, force multiplied by delta x. Since force and delta x are in the same direction, so theta is how much? And cosine 0 will be 1. With the calculator you can find out. Now this is the force. You see, according to Newton's second law of motion, you have net force is equal to m multiplied by a. So in place of force, I can write this. And I have another rule, Vf square right. I can write, if I take this to the other side, it will become minus. So it will be Vf square minus Vi square is equal to 2a del x. So I need del x, so it will be equal to this one. So instead of delta x, I can write this one here, delta x. I can write this one. So a goes with a, and I have half, this is 2, so 2 under Vf square and also as a denominator under this Vi square. So 2 I write on both sides. Why I need it? Because I have kinetic energy is equal to half mv square. So I need to write it in that shape. So half mvf square minus half mvi square, which is kinetic energy final minus kinetic energy initial, which is equal to change in kinetic energy. This is what we started here. Okay, you don't need proof, by the way, but you need to know that this is the equation we'll be using many times. So work done is equal to change in kinetic energy. We have proved it.